let's talk about the invisible force that holds our entire universe together. I mean, it keeps your feet on the ground, it holds the moon in the sky, and it keeps entire galaxies from flying apart. Today, we are cracking the code of gravity.
So our story kicks off with a classic, right? The legend of Isaac Newton sitting under a tree and bonk, an apple falls. But the real genius wasn't just noticing the apple fall down. It was that Newton looked up and started to wonder.
And this is the question that changed everything. He thought, okay, if the Earth pole can reach the top of this tree, could it reach even further? Could it possibly reach all the way to the moon? He was asking if it was the same force, and figuring that out became his mission. Now, to get inside Newton's head, let's imagine something simpler. Picture yourself whirling a stone on a string. You can feel it, right? That stone wants to fly off in a straight line, but the string keeps pulling it back in, yanking it toward the center and forcing it to go in a circle.
Well, that inward pull has a name. It's called centripetal force. It literally means center seeking, and it's the key ingredient for anything that moves in a circle. Without it, that stone would just fly off into the distance.
And here is the absolutely brilliant leap he made. Newton realized the moon is just like that stone, and the Earth's gravity is the invisible string. The moon is always trying to move forward, but Earth's gravity is constantly pulling it inward. So, in a way, the moon is constantly falling. It's just moving so fast sideways that it keeps missing the Earth, falling around it instead of into it.
So this led Newton to an incredible conclusion. The force that pulls an apple out of a tree and the force that holds the moon in its orbit weren't just similar. They were the exact same thing. And this idea became his law of universal attraction.
This is his universal law of gravitation, and they call it universal for a reason. It's not just for planets and stars. It applies to everything with mass. I mean, right now, there is a tiny, tiny gravitational force between you and the screen you're looking at. So the law basically has two main parts. The first one is pretty intuitive. The strength of the pull depends on the mass of the objects. The more massive something is, the stronger its gravitational pull. That's why we feel the Earth's gravity so much. It's gigantic. But we don't feel the pull of, say, the person sitting next to us.
Now, the second part of the law. This is a huge deal. It's all about distance. See, gravity gets weaker the farther you get from an object. But it doesn't just fade away evenly. It follows a very special rule. It's called the inverse square law. So if you double the distance between two objects, the force of gravity between them drops to just 1/4 of what it was. Triple the distance and it drops to 1/9. This little detail, this specific relationship, is the secret sauce that makes stable orbits possible. It's what holds our entire solar system together. Okay, so why was this one law such a game changer? Well, because with a single, elegant equation, Newton basically unified the rules for how things work on Earth with the rules for how things work in the heavens. He solved a bunch of ancient mysteries all at once. I mean, really think about that. The same law that explains why an apple falls to the ground also explains why planets orbit the sun, why the moon circles the Earth, and even explains the daily rhythm of the ocean tides. Suddenly, the whole cosmos seemed to follow one understandable rule.
So we know this universal force is everywhere, but how does it actually affect things falling right here on Earth? In one word, acceleration. So when an object is in free fall, it means the only thing acting on it is gravity. And here's the wild part, something that Galileo famously explored. Gravity causes all objects to accelerate at the exact same rate, no matter how heavy they are. If you could get rid of air resistance, a feather and a bowling ball would hit the ground at the exact same time. Here on the surface of the Earth, that acceleration rate is a constant, and we call it g. It's about 9.8 meters per second squared. Now, what that actually means is pretty simple. For every single second an object is falling, its speed increases by another 9.8 meters per second. Now, all of this brings us to a really common point of confusion that gravity helps us clear up. And that's the difference between mass and weight. And trust me, they are not the same thing at all. Let's just break this down. Mass is how much stuff you're made of, your fundamental matter. And that's a constant. It's the same no matter where you go in the universe. But weight? Weight is just the force of gravity pulling on that mass. And since gravity can change depending on where you are, so can your weight. Here's the perfect example. If you were to stand on the moon, your mass, the amount of stuff you're made of, would be exactly the same. You'd still be you. But because the moon is way smaller and less massive than Earth, its gravitational pull is much, much weaker. Your weight would be only 1/6 of what it is here. You'd feel incredibly light, but you'd still be made of the same amount of stuff.
So in the end, Newton gave us this perfect recipe, this incredible formula that tells us how gravity works. But he couldn't tell us why it works. What is this invisible force that can reach across the vast emptiness of space? Is it some mysterious pull? Or is it possible that massive objects are actually bending and warping the very fabric of space itself? Well, answering that question, that would have to wait for another genius and a whole other story.